So welcome back. Today's second presenter will be Jan-Erik. He's a fellow master speaker of mine. He'll tell you about that a lot. I guess we already had a WebAssembly presentation on the first meetup from Ingvar. So Jan-Erik is going to dive into more into the present and the future, probably.
Yes.
So give it away.
Oh, let's see if that works. Oh, crap. There you go. Oh, okay. One more click. Now, let's see. My fan is turning on. That's a bit better. Anyway, we can get started. All right. Nice that some people turn up. No, I'm really glad. It's a small crowd. That's good. So if I'm speaking too fast or you have any questions in between, we can do the questions in between because we're not that many. I'm Jan-Erik. I do organize stuff, mostly Rust Meetup and Rust conferences. Namely the Rust Fest. There will be one in Paris next year, so if you're into Rust, please come to the Rust Fest. I do work as a software engineer. I also give talks on behalf of Mozilla as a Mozilla tech speaker. And today I'm here to talk about WebAssembly. Who here was here for the first meetup and heard about WebAssembly? Good. Who here heard about WebAssembly on some other occasion? Good. So, I'm going to just quickly introduce WebAssembly and what WebAssembly is by giving you a bit of a history lesson. And for that, we have to start in 1995. Back then, we already had websites. And there was this new language called JavaScript, which was invented in like 10 days, which is really not that much for a language. But it was invented to and used on websites to make certain things on the website more dynamic. You could suddenly do something in the browser that the user could interact with without requiring going to the server again. So people started to use it to make funny little things on the websites. At this time of the year, you probably saw some snowflakes on the websites and so on. And this worked quite good. But the JavaScript engines back then were simple interpreters. And by today's standards, they were quite slow. But for back then, that was just enough. You had like a couple of lines of JavaScript in there. But at some point, people wanted to do more in the browser, and JavaScript just couldn't offer more. There were no APIs to do more stuff that needed to interact with the system or with the network again. So at some point, we got this massive monster called Flash and also Java applets, which now allowed us to do much more in the browser. We could do network requests. We could stream video. We had interactive games. We even had 3D games in the browser. But all of these required Flash or Java to work. And for most parts, that worked. But we also hit some pretty huge roadblocks there. Flash and Java were never really integrated into the browser. There were always something built on top. And their interaction with the website and the Flash was always a bit shaky. And at some point, we also had a lot of security bugs with Flash and Java running in the browser. And so people wanted to get rid of it again. So people got back to JavaScript again, used it more and more, and they started to build real big applications in the browser. But with more JavaScript in the browser, we also needed faster engines to execute the JavaScript. And that's when V8 came to life in 2008. Which was one of the very first JIT compiler engines for JavaScript, which really speed up JavaScript execution in the browser. And at that point, people moved everything to the browser. From the simple mail application that you know as Gmail now, to large video or photo editors right in your browser. You got pretty much everything that you had as a native application before. And people at some point even took other languages and compiled them to the browser, mostly to JavaScript to run them in the browser, because they weren't happy with writing JavaScript. But for a language that was designed and implemented in like 10 days, it was never intended as a target for a compiler. So it couldn't, it hadn't all the features one would have, one would want in a language that you compile to. So people thought about what they can do with JavaScript by removing a bit of the features in there. And that's how asm.js came to life. asm.js was intended as a subset of JavaScript that reduced it to just a simple core, but that would allow to be much more optimized once the browser detects this special mode of JavaScript. And it did so by mainly two main features in the specification, or in the subset that was used. And that are type annotations and a flat memory buffer for all your data. So let's quickly look at what that is. Who here writes JavaScript or did write JavaScript at some point, knows a bit of JavaScript? Well, that's enough. I mean, you're probably all programmers at some point. So you will understand this function. It's called add. It has two arguments, x and y. It calls the plus operator and returns the result. If you input two numbers, that's pretty easy. You call the plus operator and two numbers, which is just the sum of the two numbers. But if you input two strings into this function, you will actually need to concatenate these strings, which is a whole other operation than the sum operation. But the JavaScript engine knows how to do that. But now if you pass in something other than a string or an integer, like an object or an array, which is also just an object, and something completely different as well, well, you're pretty much out of luck. Something will happen, but I'm pretty sure it's not the thing you wanted it to happen. So there's a lot of going on just by calling the plus operator on two unknown things. But if we could tell the compiler that we're only dealing with integers, it would be much easier to run this code, because then we could just drop down to the instruction of your CPU to do this sum operation of two integers. But for that, we need some way to say that we have a certain type. And JavaScript does not have that. But what JavaScript has is certain annotations. And we can now add these annotations to tell the engine that's running the JavaScript what's happening. Here we just used the binary OR with a 0 to tell it, well, we're dealing with integers. A binary OR only makes sense when we have integers. A binary OR with a 0 doesn't change the value. So at this point, we're telling the engine, well, we're expecting two integers as input, and we're also expecting integer as the output of this function. And the engine can now go, compile this function down to the instruction on your CPU, and execute it right away without dealing with the different types. It only has to deal with this problem once it detects that it doesn't get an integer. But if you do this through your whole code, you're never dealing with not integers there, so that's fine. The other thing I mentioned is the linear memory access. If you're writing JavaScript, you're probably not thinking about memory too much. You're just creating your objects and your strings and your integers, using them, and at some point not using them, and you can expect that the JavaScript engine will at some point just remove the data that's not in use anymore. And that's done by the garbage collector. But the garbage collector runs randomly at certain points, has to stop your code, go through all the data, look at what data is unused, remove that data from memory, and then resume your code. These stop times that it needs to do are quite unpredictable. And for certain algorithms, it's just not acceptable that your code is stopped at some point. So you don't want that. So what you can do in asm.js instead is just use a huge buffer of memory. From the point of view of the engine, this buffer is always in use. So there's no need to stop your program and remove the memory. You can just use the buffer now. But now you have to place your data into this buffer somewhere. And now this is completely up to your application, how this buffer is used. If you're coming from a C background, or even Rust, this is pretty similar how the heap is handled. They also only have some opaque pointers into some memory, and you have to deal with this yourself. In C, you have, for example, malloc and free, which do the heavy lifting for you, so you don't actually have to track it yourself, but malloc does that for you. But now this perfectly maps to asm.js. People did use that to some extent, and they built on top of that, but they had other roadblocks, mainly because it's JavaScript, and JavaScript does not have all the features we want. So that's when they sat down and thought about what they need on top of that. And that's when WebAssembly was born, basically as a successor of asm.js. So what is WebAssembly? Well, WebAssembly is a binary executable format for the web. That means you can take some other code, compile it to WebAssembly, and run it in your browser. WebAssembly is also a general purpose virtual architecture. It's comparable to your x86 code or Java bytecode. It basically gives you a few operations and the semantics of these operations, and the engine implements that and can execute it. It's also modeled in a way that it's easily transpilable to actual x86 machine code. So there's not a huge step from WebAssembly to actually running on your CPU. WebAssembly is also a compiler target. The idea is that you take, for example, C code or Rust code, throw that into your compiler, and out you get some WebAssembly code. And WebAssembly is now an open standard. It's developed in a W3C community group. And the best thing about this is that all major browser vendors are on board with this. So there are people from all major browser vendors sitting in this community group discussing what features WebAssembly would need and how to implement them. And by now, it's enabled in Firefox, in Chrome, in Edge, and in Safari, and even in mobile Safari. So you pretty much can use WebAssembly everywhere by now. When speaking about WebAssembly, we also need to think about what WebAssembly is not. Because people tend to confuse and get a bit too excited about WebAssembly. WebAssembly is definitely not a replacement for JavaScript. It will happily live side by side with JavaScript for the foreseeable future, and none of the applications that you're using today will be rewritten tomorrow to WebAssembly. It just doesn't make sense, and WebAssembly is just not future-rich enough to handle that right now. WebAssembly is also not necessarily a programming language. You can write the assembly instructions yourself, but just as you wouldn't do that for your x86 or ARM machine, except in very extreme cases, you don't need to do that for WebAssembly, except maybe for learning. WebAssembly is also not a target for every language out there yet, especially for languages that have a heavy runtime and a lot of additional features on top. Things like Java, or even JavaScript itself, or Ruby or Python that have their own runtime and garbage collector bundled with them are not easily translatable to WebAssembly by now. It will get easier in the future, but for now, C or C++ and Rust are the main languages that you can use to target WebAssembly in the end. Now you might wonder, why do we need WebAssembly after all of this? Couldn't we just use asm.js? It had a lot of features. But with WebAssembly, we can now write code that's a lot smaller than asm.js. It's a binary format, and the encoding is especially made in a way that most things that we need to put in there are pretty encodable in a very few bytes. And that also makes it a lot faster to parse. Even though JavaScript itself is not that huge of a language, it's still very hard to parse. With WebAssembly, it's a lot easier. Basically, you just need to go through the WebAssembly code once, check that it adheres to the encoding, and then you can compile it. And with WebAssembly, we now also have the freedom to extend the platform with the features we needed. One thing, for example, in JavaScript, we still don't have our integers above in the range of 64-bit or even larger. With WebAssembly, we will have these natively. And for WebAssembly, there's a formal specification that all browser vendors agree on. We didn't have that for Flash. It was just implemented once. We didn't have that for the Java integration into the browser, really. And even for asm.js, not every browser implemented that or agreed on the specification. So for WebAssembly, we now have a specification. It hit version 1 earlier in the beginning of this year, and all browsers implemented that. And we can be pretty sure that they continue to implement the same thing. So let's see how to use it and how to actually use it for Rust. would have, if this meetup would have happened like 3 weeks ago, I would have advised you to use mscripten, which is an LLVM-based compiler that can translate C or Rust code to JavaScript or asm.js or even WebAssembly. But we don't need this anymore. And the last time I gave this talk, I also used C as an example because it was a bit easier then. But we won't write C. It's a Rust meetup. So we're going to write Rust. And thanks to this pull request to the Rust language called add a new wasm32 unknown target, we now have a target in the Rust compiler that allows us to compile Rust natively to WebAssembly without additional tools. This actually landed in the Rust compiler a few days ago. It's already in the nightly compiler, except that the LLVM side is not prepared for that, but that should happen in like 1 or 2 weeks as well. So you kind of can use it, but you still need to hack a bit around that. I'm going to skip about the hacking part and just show you how you can actually spit out WebAssembly. So anyway, this is some Rust code. We're going to greet Budapest. Good evening, Budapest. Return that as a string. Right now, we still need to basically write a binary, so we need a main function, even though it will be removed later. This is just for the compiler to do the right thing. And there's a few interesting things about that. First, we need an attribute called nomangle. By default, the Rust compiler will use a mangle algorithm to don't duplicate any symbols in the compiled file. But obviously, we want to call this function greet, and we need to have the name greet in the final executable. So we don't need to mangle it. We also want to give it a certain ABI, and we're using the same ABI as C does by using extern C. This basically just defines how we pass arguments back and forth between functions. And we're returning a static string here, which will be important later. So now if you want to compile this code with Rust to native code, you just call rustc, let it optimize, give it the file, and it does its thing. It will not do anything because the main function is empty. But we can compile it to WebAssembly now with this new target, which basically means we pass a few more flags and it will do the right thing. We then need to actually garbage collect the WebAssembly file a bit because right now we don't have any optimizer in there and there will be a lot of useless crap in there. So this step will go away once the linker from LLVM is actually capable of doing WebAssembly itself. But for now, we can remove a lot of the stuff in there using wasm.js. And once we've did all this, this is what we get. This is the hex encoding of a small part of the WebAssembly module I just compiled. And you can already see a few things. If you can read hex, you might actually see that it starts with ASM. This is just a magic header in the file telling basically the browser, the engine, that it's actually a WebAssembly file. If you look a bit further down, you see more words. There's some word about memory in there. And further, there's the greet function in there. It's basically just the name for a function that we export from the WebAssembly module. Reading hex code is really hard. So when WebAssembly was built up, they already thought about that there needs to be a text format of the same code. And there are now also tools that just translate from one format to the other. We can format to the WAP format, which is the text format of WebAssembly, using a tool called wasm.js. If we do this and look at the code, we basically see a Lisp-like language that encodes the same things as the binary before. We have some metadata in there. We have the export of our greet function in there with some additional annotations, and then we have the code. Now, this is the code that actually returns our string. Can anyone guess what's actually happening there? I gave a small hint by including the data part as well. So the thing about references in Rust is that they're most of the time what's called fat pointer, and it's actually just a pointer to some data and the length of the data behind this. whereas in C, you usually just have a pointer, and it's up to you to figure out how large the object behind that pointer is. In Rust, most of the time, you get the actual length. So what this code is doing, it's actually getting a parameter, which is just an integer, as an input parameter. It will then store the length of the value, our string, which is 21 bytes long, into the lower 4 bytes of this past index, and will then store the pointer to the actual data in the upper 4 bytes. I have no idea why it does it that way. It could just do it the other way around, first store the pointer, then the length. But that's just how the code compiled now. It doesn't really matter. But what we will have in the end is we need to pass it some pointer to some form of memory where it will write two values, the pointer to the actual data and the length. Now this is the module that we have to actually execute it from the JavaScript side and get access to this data. We need to do a little bit more work around that. So we have a few helpers. This is, again, a bit of JavaScript. It basically just gives us the memory that we need for our two values. Now, we need two, as I said before, the pointer and the length. And we are using a 32-bit architecture here, so we just pass it twice 4 bytes. This alloc function is actually a pretty simple allocator that's exported from the same WebAssembly module, which I haven't shown before. It basically just gives you a block of memory in the memory buffer that Rust sees. And if you know C, you pretty much know already that pointers are just numbers, and that's how they are handled in WebAssembly as well. Now, we need a few more bits of code on the JavaScript side as well. You don't really have to understand this code, but basically what it does, it reads out the data from that we passed in before, follows the pointer to the actual data in memory, copies out the number of bytes that the length specifies, turns that into an UTF-8 encoded string in JavaScript, and returns that. It's still a little bit of banging around with that, but you basically write this code once and then can use it from the JavaScript side. So you can actually interact with the WebAssembly module. Now, if you want to execute that in the browser, you have this nice little API for handling WebAssembly. Basically, you fetch the data from the server. You turn that into an array buffer, so you have the actual bytes. Then you call the WebAssembly module, where you call the compile function and give it this buffer. And the compile function actually does not compile anything. It just checks that it's valid WebAssembly. From that, you then need to instantiate a module, which then actually compiles the code and gives you back an object which also has all the exports on there. So with all the code we had from before, accessing the exports, allocating some memory, letting the WebAssembly module write the code in there, reading out the data again, we can now execute the code. And if we execute this code in the browser, well, it works. Now there's a bit more code than I've actually shown. The slides are online. It's actual JavaScript in there, so you could read the source code if you want. If you don't want to view the slides, I made the site hellorust.com, where I will collect all these things in the future, how to make it happen, what's the different pieces you need there. It's pretty bare bones right now, but over the coming weeks, I will extend this quite a bit. So, what's missing from this? Well, this just landed, the new target just landed. Pretty much most of the parts from the standard library of Rust are currently just returning nothing. They're basically just crashing because there was no time and no sensible way to implement this. Basically, everything that handles file operations or network operations or anything that a real operating system would do for you are not in the standard library for this target because WebAssembly has no notion of that. You will need to interact from the JavaScript side anyway, and we're currently figuring out how we will actually do this. My idea currently is that we take a lot of what mscripten already did, put that back into some JavaScript bridge and have this code that way. That's exactly what's missing there as well, the JavaScript implementation of certain functionality, so we can actually print data, that we can actually do some form of file operation, for example, mapping this to some API in the browser, either the file API or doing this in the local storage, or some form of mapping some common functionality in Rust code to some operation in the browser. We also need a lot more testing. Basically, this will just be, well, enable testing for my crate at some point. We have some ideas that we will do this on all crates that are published on crates.io at some point, so we can actually see how much of WebAssembly is already working. But if you're interested and want to see what works and what does not work, just play around with it. It's really fun to experience a lot of bugs in libraries that were never intended to be compiled to the browser and see what breaks. I did that for certain libraries and fixed bugs, and in the end, it also fixes real bugs in these libraries anyway. And of course, a lot of documentation and tutorials and examples are just not there yet. I intend to put a lot of this onto hellorust.com, but people will experiment with this and write more tutorials. By now, there are a lot of tutorials for the old way out there that are still a lot of hacks involved, and half of them are probably not working anymore either. So we will need to write more documentation, bring the ones that are out there up to date. My personal idea is also that Webpack will have easy integration with WebAssembly and Rust. They already have integration with WebAssembly, and they're trying to figure out how to do that as efficiently for the developer and for the compilation process. And my idea is that at some point we can just drop our Rust files into a project and call Webpack, and Webpack will also just compile everything, wrap it up into WebAssembly module, export the things to your JavaScript modules, and there you can access it. This is a lot of things that will happen in the future, but I'm really excited about seeing this happen. So, thanks. Do you have questions?
Will WebAssembly have multi-threading?
Yes. So that's like basically one thing about WebAssembly. The version that we currently have enabled in the browser is intended as an MVP, as the most viable product that they could ship this year. But there were always ideas to add new features, and it was built in a way that these features could be added. It was just a matter of designing these systems. And actually the threading, so there are RFCs out there proposing different implementations of threading support. And there's one that's currently in a pretty late stage, so it will get implemented in 2018. So by the end of 2018, we will probably have proper thread support there.
Who do you think the early adopters will be of this technology? So the earliest.
So that's really hard to say, but so what I think, like for everything that's doing anything performance-wise in the browser, the very first examples and demos out there are always games, because they benefit a lot from these performance wins. So there are already game engines, 3D game engines compiled to WebAssembly running in the browser. I think it will be quite interesting to see a full-blown game that you can run in the browser without needing to install anything besides downloading the resources once. That will be one thing. I also know about a few projects trying to do certain video algorithms in the browser. For once, you saw me interacting with the demo at the beginning, which was basically doing some filters over some live video. That will be quite interesting. There's a new codec in development. They want to use WebAssembly to test out this codec in the browser and share samples of the running code through just putting WebAssembly on the side. So you can actually share this running code with people and debug it. So I think these multimedia applications will be one of the very first things that will make heavy use of it. The other thing I see is, for example, Ember is rewriting their Glimmer engine, which is basically their engine that does all this DOM diffing and rendering. They're rewriting this in Rust and compiling that to WebAssembly because they actually see their Glimmer engine as one of the bottlenecks right now, and they want to speed it up by just shipping it as a WebAssembly module. Any more questions?
Cool, Dan. Thank you very much again.